Really glad you're here. I'm Laura Steinberg. I'm the Seidner Executive Director of the Schiller Institute for Integrated Science and Society. We're very happy to have you here at this kickoff event for this semester's Distinguished Lecture Series at the Schiller Institute for Integrated Science and Society. This is a series in which we bring in to speak world-renowned thinkers who talk to our students, faculty, and staff about their work in the areas of energy, environment, or health. Our format today will be a talk of about 40 minutes, followed by 20 or so minutes of questions and answers. Following this hour, you are more than invited to stay for a buffet lunch that we're serving in the back of the room, which will be catered by Banh Mi. And so you're invited to stay and have informal conversations with each other and with our speaker over very tasty toasted baguettes and spicy noodles and tofu and chicken and all sorts of good foods. So again, really happy that you're here. These lectures are designed for everybody on campus. They're designed in a way that you'll be able to come into contact and learn about results of important work in ways that will be understandable to anybody on campus. And that really matters to us as the Schiller Institute. So let me introduce to you our guest for the afternoon. Our guest is V Balaji, who likes to go by the name Balaji, as I've come to learn. Balaji is a distinguished fellow and leader of the Climate Institute at Schmidt Sciences. So Schmidt Sciences is an international philanthropic organization which was founded by Wendy and Eric Schmidt. You may know Eric Schmidt as the former CEO of Google. The Climate Institute that Balaji leads at Schmidt Sciences represents one of the key focus areas of the organization. The others at Schmidt Sciences include AI and advanced computing, biosciences, and astrophysics and space, all of which are essential to Schmidt Sciences' stated mission of supporting a thriving world. I point this out because the Schmidt Scientists' mission of supporting a thriving world sounds a lot like and entirely consistent with what Boston College is about, what the Schiller Institute is about, and really what I think probably the work and the thought that many of you and probably all of you here is about in being part of Boston College. So give you a little bit more background about Balaji. He joined Schmidt Sciences in 2022 after a 25-year career at Princeton University, where he served as head of the Modeling Systems Division of NOAA's Geophysical Fluid Dynamics Lab. He holds a PhD in physics from Ohio State University and a master's in physics from the Indian Institute of Technology in Kanpur. In 2017, Balaji was among the first recipients of the French President Macron's Make Our Planet Great Again award, and through that has an academic appointment at the Sorbonne University in Paris. He has served on numerous U.S. National Academies panels related to climate, computing, and geophysical data, and has been on scientific advisory boards to several U.S. agencies and climate research institutions across the world, including currently to the UK Meteorology Office. So as the leader of the new Climate Institute at Schmidt Sciences, Balaji and his staff are building a framework for analyzing pathways towards a carbon and resource neutral future through linked programs on climate modeling, land and ocean carbon, global freshwater, and energy planning, with an eye to the global south. So that said, I would love to introduce you, and I'm looking forward to talk by V Balaji.
So my background, I think Laura gave me a very generous introduction. So my background is basically in computational physics and climate modeling. So that's where I started my work. Since then, as you heard, since I joined Schmidt Sciences a few years ago, and I started advising them even a few years before that, I was given more or less a free hand to say, design us a climate portfolio for our funders. And it started from climate modeling and has gone into all the areas where applying the models to understand the water and carbon cycles and eventually to understand how we shall deal with the climate crisis. So the premise of this is somewhat optimistic, and I understand that recent political events don't warrant optimism, but assuming that one day we are taking this problem seriously and we are going to try to bend the carbon curve, I want us to be sure. Right now, for various planned approaches to addressing the carbon problem, I couldn't even tell you with confidence what the sign of the intervention will be. Will it actually move carbon downwards or upwards? There's a lot of uncertainties in the system. We understand where the emissions come from, why they cause the warming, but some of that emissions is going into the land and the ocean. We don't understand the coupled behavior of the whole climate system very well. So I'll walk you through how we can use models to understand these things, and I hope it'll be approachable to a wide audience, because models are changing in very major ways in the current period we're in. This started a few years ago. I started dabbling in machine learning in around 2015, but now there's a lot of work going on in this field. So let's start with what climate models are, what climate is to begin with. So the first thing is what we say is climate is what you expect and weather is what you get. So the expectation is based on observing the climate of what happens over a few decades. The official definition, which is produced by NOAA, is the average of the last 30 years of weather, which is changed every decade or so. So that's considered the normal, and then any deviation from that is considered weather. So the climate is what is normal, but the expectations do keep changing. Decade after decade, the baseline against which you measure climate change changes. What you personally perceive is the difference between the weather and the climate. So on a given day, so if supposing it were, it's not, but so assuming it were 50 degrees Celsius outside today, you would, because your expectation is in January, that's a very warm day, you would call it a warm day. But the same temperature, if you measured it in July, you would say it's a very cool day. So the expectation of what you expect and what you actually see is what you perceive. That's a small difference, right? So the climate change signal we are hoping to observe is on the order of a degree per century. Whereas on a normal day, you see 10-degree fluctuations in temperature between day and night. So we are removing all this weather noise, what we consider noise, from the signal to look at the underlying trends. That's what we're trying to do in climate. So the residuals we're trying to measure are very small. So it requires a lot of fairly precise work with observations and models. The other thing is that there's a typo in this, but there's fluctuations and feedbacks and forcings at all time scales. So there are short time scale things that happen in clouds, for example. Clouds are one of the biggest unknowns in the climate. And clouds can be more or less reflective depending on the size of the water droplets that make them up. So they can be very white and bright clouds that reflect a lot of heat, and their net effect is to cool the planet, or they can be dense and dark and their net effect is to warm the planet. So this can happen on the cloud scale. If you go to very large scale ocean circulation, for example, the exact position of the continents matters to the ocean circulation. So you can say that megacontinents, the evolution on million-year time scales is also important. Microbes can play a part in modulating how carbon is taken up in the land or in the oceans. So my basic pitch to students in the audience is that if you're going to work on climate change, it doesn't matter what field of research or what field of study you're currently in, your work is relevant to the climate problem. Everything is connected to the climate problem. That's what makes it unique. That's what makes it uniquely challenging, because we're trying to come up with a solution to the only planet we have. And you cannot do very major experiments with it. You have to understand it without doing real experiments. But almost anything you're interested in, whatever you consider your interest, I think you can work on climate change. So let's take a look at the history of the climate record. So let's start with this. So this is temperature of planet Earth going back 500 million years, shown in a time series. The black horizontal line is the average present day temperature. So relative to that, you can see all the fluctuations. The time scale keeps changing, so please pay attention. This is like hundreds of millions of years in the past, then it goes to tens of millions, then single millions, then less than a million. So you have this very large warming. There have been times in the Earth, on Earth's history, when it was like 14, 15 degrees warmer than today. So warm temperatures have been seen. So there's even this little spike which goes up to around 17 degrees warmer than today, which is called the Paleocene-Eocene thermal maximum, or PETM. So at this point, we had equable temperatures. That is, there was not much change in temperature between equator and pole. The poles were very warm. We have records of crocodiles and palm trees and all near the poles. Then there is a long and gradual cooling that goes over hundreds of millions of years. Hominids appear somewhere in this period, 3 million years ago or so. And then we get into this period of ice ages, right? The Pleistocene. Now we've gone down to less than a million, so the time scale has changed. And you have these cycles, and it has to deal with the tilting of the Earth's orbit. So it has to deal with orbital mechanics of the Earth. So you can kind of get to what the Milankovitch cycles. So you can kind of understand what causes these fluctuations. And these are the ice ages. And the humans do exist on this planet, but they are nomadic because they follow the ice sheets. When the ice sheets migrates equatorward, they migrate equatorward, and when it recedes, they migrate back poleward. The last ice age, the thing that's marked here as the LGM, is the last glacial maximum. So 20,000 years ago, we had a glacial maximum. The Laurentide ice sheets in the north extended down into Pennsylvania or so. So all these areas, this area would have been under several tens of meters of snow, probably hundreds of meters of snow. And then there's a gradual warming, so it still looks like an ice age. Something happens around 10,000 years ago, and the climate becomes remarkably stable for around 10,000 years. And think about this, that's what makes almost anything we consider civilization possible. Settlements become possible. You can live in a particular area and know that the rivers will contain water next year, as it does this year. Agriculture is possible. You can plant crops and you know the cycles of the seasons, you know what you can do with that. None of this is possible in a fluctuating climate. It's possible in a stable climate. So almost all of civilization as we know it is compressed into these 10,000 years, and then you see what happens right at the end. The CO2 is spiking again since the Industrial Revolution. So that's what we're dealing with. If you look at the last period in very high resolution, you have these areas. If you reconstruct the temperature, you'll see some fluctuations. It goes up and down by a degree or so. And then again, towards the end, you see a spike. These temperatures, obviously, you don't have direct temperature measurements. You're reconstructing them from proxies by measuring the rate of growth of trees, for example. And we know certain things existed like the medieval warm period. This is all based on European data. There was a period when it was slightly warm. There was a period which is called the Little Ice Age, when it got very cold. There's records of the Thames being frozen in July, for example, in some summers. It never unfroze. So these are probably regional signals, but now we have a global signal. Wherever you look, pretty much it's warming. And this has happened before in the past as well, and there is a link to CO2, which you see here. So there's a historical event which is called the Great Dying. It's probably the greatest episode of human death in history. So around 1600s or so, when the conquistadores arrived here, they brought with them a lot of pathogens. And there was a flourishing agricultural pastoral civilization here. They essentially destroyed it. The estimate in this paper is that 56 million people died in the course of a few decades. A lot of agricultural land returned to forest. That means it was pastured and the trees grew there. So around the same time, you can measure a decline in carbon measured in Antarctica. So this link between carbon and temperature, you can see back then. And you can even look at these ages and then look at the Little Ice Age and ask yourself, I don't think we have a definitive answer. Is the Little Ice Age actually caused by the fact that carbon was drawn down because of a civilizational collapse in the Americas? So these linkages can be seen. So humans have been affecting this for a while. The reasons for this became clear. So Eunice Foote wrote a paper in 1857 that was recently discovered around 10, 15 years ago. Usually this initial discovery is attributed to others. Men, but she not only wrote the paper, she did these experiments with bell jars where she added CO2 to one bell jar and exposed it to sunlight and showed that the temperature in the bell jar with excess CO2 was warmer. But she understood the implications of that, and she said an atmosphere of that gas would give the Earth a high temperature. So this is something she said back in 1857. Now we look at, okay, what happens? What happens if we keep adding CO2? So the first thing you see is how the Earth's radiation budget, how temperature is distributed around the globe, how radiation in particular. So the blue curve is the radiation coming in from the sun. So the Earth, you think of the body, is being heated by the sun's rays and is cooling towards space at the same time. So doing both things. Eventually, it'll come into some equilibrium. That is not evenly distributed. So there's excess heat near the equator, which is where it gets most of the direct sunlight. The most of the heat leakage is closer to the poles. So the deficit is near the poles, there's excess near the equator. So somehow this energy has to be redistributed because of conservation of energy. All the excess heat near the equator has to be moved towards the poles on a spinning planet, on a tilted spinning planet, which sometimes wobbles. That's why you get ice ages. So if you put all this in and you try to solve the equations, you get a global atmospheric circulation that looks something like this. You have these things called the trade winds, which blow west to east across the tropics. It's called the trade winds because in the era of the sailing ships, sailors relied on this to travel. And this converge and push the air up, so moist air goes up, you get a lot of convection, you get a lot of clouds, you get a lot of rain. So normally in the tropics, you find rainforests, you get a lot of vegetation. The air that goes up has to come down slightly away towards the poles. So in both hemispheres, if you go a little away from the pole, just outside the tropics, you'll get deserts because there the air is going down, so it's very hard to make clouds go and make rain. And so you get this circulation, so you get westerlies about that. You do the same in the ocean, you get, because of the continents again, it becomes a much more complicated system. And it's a very slow system. It's something to keep in mind. And this whole thing was at one time called the global conveyor belt because it travels around, the water travels around the whole globe and it transports heat. The red colors is warm water. So you can see that warm water actually transits the whole globe. And then somewhere when it reaches the North Atlantic, it becomes both salty and cold, and that makes it sink. And then there is a reverse flow underground. So this is called the meridional overturning circulation. It's very important for the climate. That's why I'm mentioning it. This is a very slow circulation. So do you have an idea if I put a parcel of water and allowed it to make the whole circuit, how long it takes? Somebody make a guess. How long would it take a parcel of water take to do the whole circuit of this conveyor belt?
3 years.
3 years.
1,000.
It's about 1,500.
Oh.
Yeah. It's a very slow circulation. So heat and carbon, if you can actually get it into the ocean and get it into the deep ocean in particular, it will stay there for a long time. That's one of the things that is actually keeping global warming from CO2 being worse than it is today, is because a lot of it is going into the ocean. The ocean is acting as a shock absorber and keeps absorbing. So a key question is, can it continue to do that? And what happens to the ocean if you keep adding heat and carbon to it? So how do you actually compute this stuff? So you have all these circulations. We have these equations we can solve. They're kind of hard to solve. So in 1922, Richardson came up with this idea that this is a theoretical thing where he said there'll be a machine and there'll be computers, which means people who actually do calculations on pen and paper, they were called computers. And they would be situated in this, they would be all sitting there in the sphere. And the central person would shine a light and say, okay, it's your turn. And then you do a calculation, then you pass it to your neighbor. So that's how he conceived of it in 1922. But then digital computers came along. We could pretty much do this, excepting with chips. So you have chips and they're in arrays and you can pass calculations back and forth. And at the Institute for Advanced Study in Princeton, the 1950s or so, von Neumann invented the digital computer. The first thing he wanted to do with it was actually study weather and climate. That's the first application he thought for it. He was a Cold Warrior. So let's remember, he wanted to do it because he wanted to weaponize weather and climate. He wanted to cause droughts in the Soviet Union, or he said, if I want to direct a tropical cyclone to divert from its path and go somewhere else, what will I do? A thermonuclear bomb. Set off a nuclear bomb and it'll move the path. And he wanted to compute all these things. He said, where can I put the bomb so that I can direct this? So he wanted. Leaving that aside, why he wanted to do it, a lot of great science came of it. So Charney, he's a young man here on the left, kind of was the founder of our field. And he and von Neumann wrote the first paper together, which was the first numerical weather forecast, 1950 paper. And this computer was again programmed by people who had to actually wire things together to actually make this. So then the second stage was making a program. This was wiring by using programming by actually using wires, and then an actual programmable computer came about. And then he also asked this question about, if I do this forecast model for forecasting weather and I keep running it forever, what would happen? That was just, he called it the infinite forecast. He just opened it as a thought question. So Manabe is a scientist whom Yi and I both have worked with in the past, who worked at the same lab as us. And he asked this question back in the 60s. And so this is the vertical distribution of temperature, right? So as I said, the Earth is cooling to space, so it keeps cooling. And at the same time, convection keeps trying to move. When it cools, you get stratification. That means the temperature changes with height. And convection tries to equilibrate it, tries to bring it back into a mixed state. So it's trying to balance between these two things. It's called radiative convective equilibrium. And if you run it long enough, you'll get a profile that looks like this. What Manabe showed was that if you keep increasing the CO2 of the atmosphere, then the radiative balance of the atmosphere changes because it's a greenhouse gas. And he showed that the surface temperature actually warms if you keep doing this. So the first key result showing that actually adding CO2 is going to cause warming. Then he built a model with the land and ocean because you have to bring the full system into it. And he showed, well, in a couple system, the same thing happens. So the dots are some observations. This is latitude and temperature. So it's the temperature is a function of latitude. For the standard atmosphere, you get a profile of temperature that looks like the black curve. And if you add CO2 everywhere you go, it becomes like a couple of degrees warmer. Now it's saying, okay, CO2 is warming everywhere. What do we do with this information? So Charney by then was a senior scientist. In '79, he was asked to produce this thing called the Charney report, Carbon Dioxide and Climate, a scientific assessment. It's based on a very few model runs. There were only two centers capable of running this. One was GFTL, where Manabe did it. Jim Hansen did it at a lab called the Goddard Institute for Space Sciences in New York. And they showed some basic results, which still hold true. But one of the interesting facts is the sum of all the stuff we say that CO2 is going to cause warming and is going to cause this much warming, all of these things were pretty much said in the 70s. We know that now from even looking at internal literature from Exxon and so forth, they also knew about this stuff. So the direct effects of CO2 are actually fairly small. It's 4 watts per meter squared. What makes it worse is there are all these feedbacks that amplify this. There's a water vapor feedback. Warmer air holds more water vapor. Water vapor is a greenhouse gas. So warmer air is also a warming agent. So that's a feedback. Ice reflects heat. If you reduce the amount of ice, you reduce the amount of heat reflected. That's another feedback. If you put all these feedbacks in, you come up with a range that for a doubling of CO2, you're going to warm between 1.5 to 4.5 degrees. Some of the big unknowns are the clouds and so forth. So this is still true. If you fast forward to today, and this is actually a little old by now, this is AR5, we're already almost at AR7. But basically, we have a lot of modeling centers around the world, and they do this they try to predict the historical warming period from the 1950s on, actually started 1850s, but we're just looking at the last 50, 60 years. And then you project that into the future. And now we're getting into scenarios because we don't know what humans are going to do. So one is that they don't do anything. So that's the business as usual scenario. And you get like several degrees of warming. A second scenario you can hope for is that there is actually, through some mechanism like carbon taxes or tariffs or something, you come up with a mechanism for controlling the amount of carbon we emit, and then you can stabilize the temperature. Now, they have lots of models now. Back then, it was only these two models. And if you look at the computers have been getting bigger and bigger, and you can do more and more things have been found out about this system. So this is the history of GFTL computing, starting from John von Neumann going up till today. I won't get into the details. The model's becoming more and more detailed, and detail means two things. One is the resolution. This is the first. IPCC has these every 6 years assessment reports. So the first, second, third, and fourth assessment reports, you can see what the typical resolution of a climate model, how it changed. This is a map of Europe. And it also changed in detail in terms of the complexity of the processes. You initially have just CO2 and sunshine and rain. Then you add clouds, then you add some chemistry, you add an ocean, you add like sulfates, you can keep adding things to it. So you add both complexity and you add resolution. Together, I call them adding detail. You keep adding details to the models. The other thing you can do with models, you can explore things that didn't happen. So you can explore counterfactuals. So this is a paper that he probably remembers fairly well. So if you look at the Indian monsoon, the historical trend of the Indian monsoon, which is just measured over this area, the Indo-Gangetic Plain, is a long-term slow decline. And you can attribute it in the model. What you can do is that there are many things that cause warming or cooling. So there are natural mechanisms like volcanoes and changes to the solar forcing. There are aerosols, which are particulates which dim the planet. And then there's greenhouse gases which warm the planet. You can separate all these causes. In a model, you can turn one of them on, turn the other one off, and so forth. You can do all these things. Sorry, I went going too fast. And you can do these studies of attribution. You can say, okay, what is actually causing the long-term decline of the ocean, and what is going to happen under CO2 warming? You can probe all these questions. So the important thing, the result itself is interesting, but the more important thing is that you can look at things that did not happen, counterfactual stuff that you cannot measure in the real world. So you kept adding these details, you kept building these better and better models. You're exploring a lot of things. You're exploring all these counterfactuals. Computing changed in a certain way. So what happens will be, you're probably hearing that computers are continue to get bigger and faster. It's called Moore's law. So they're following a logarithmic curve for the last several decades. Computers have been growing exponentially, meaning every 18 months or so, you get a doubling of computing capacity. But that's capacity, the actual speed of arithmetic, which is the green curve flattened some years ago, it's just a physical limit. You cannot make transistors much smaller than you're making them today. So that's changed the kind of computing. So people are turning more and more towards using this as a prediction tool mainly. So this is what are models for. So you can solve initial value problems. If I tell you the initial state, predict what's going to happen in the future. The problem we are also interested in is the forcing change. Or change the amount of CO2. How is the climate of the system going to evolve? It's not so much a prediction as to knowing how the system behaves when you change something outside to it. And then there are areas in the middle, like where you have to consider both changes in initial values and changes to the boundary conditions. So weather and climate often are spoken about together because the same tool that you use as the weather model, von Neumann said infinite forecast, just run the model forever and see what happens. That's a climate model. But now we have to look, since there's two different classes of problems we're trying to solve in the machine learning era, is this still a wise thing to do? So let's see so this is the same result as before. Then I'm showing this is done with a one-dimensional model. It's just heat and carbon in the vertical and water vapor. Then you can build a GCM with all these general circulation models. So you can model the circulation of the ocean, circulation of the atmosphere at a certain resolution. Anything that's not resolved in the model, because the computers only limit the amount of resolution you can add. You add everything else and you call these parameters. Anything that is not resolved by the model, which is happening at a too small a scale, you try to guess what you come up with theories, not a guess. It's a theory of what the aggregate behavior of clouds will be, and you try to put that into a model. So these are called parameterizations. And the model resolution does not evolve very fast. And that's because, as I said, the arithmetic did not get faster, even though the models got bigger. So you can build bigger models, but you can run more copies of the model, but you can't change the resolution of the model. So a GFTL, for example, starting from the first couple model we built from the 1969 paper to the 2019 paper of the fifth generation of the climate model, the resolution changed from like 500 kilometers horizontally to around 50 kilometers. Meanwhile, the weather forecasts have been getting better and better. So they call this the quiet revolution. So this is a much reproduced figure. It's basically showing that the weather forecast model of the, let's say, what can I pick? So a 3-day forecast, or rather a 5-day, a 7-day forecast of today is about the same quality as a 3-day forecast in 1980. So that's the extent to which weather forecasting has improved. And with machine learning, weather forecasting is actually going through essentially a second revolution right now, right as we speak. Machine learning turns out to be really good for the modern day computers, which the arithmetic, as I said, is static, but you can do lots and lots of it. The capacity of the machines is intense. So what machine learning does is that if you're computing the relationship between the reds and the blues, you're computing some sort of, trying to see how the blues depend on the reds. So you're trying to compute some kind of regression between some inputs and outputs. You can at will increase the complexity of the interior model. You can add as many neurons as you want. So each one is called a neuron, and it's some kind of relationship between this and that. So it's multiplied by something, add something to it, keep going like this. So you can see by the density of the black lines, each one represents a computation. So you can add lots and lots of computations to compute the same relationship between, in this illustration, the reds and the blues. So it's very, very good at doing these. The GPUs in particular are extremely good at doing this kind of calculation. So what you're doing is, instead of coming up with a theory of how the blues depend on the reds, how your outputs depend on your inputs, you just throw a lot of arithmetic at it. It will just compute. If you have enough data, it will compute all. If you have to have enough data to fill in all the values so that you can do these black line computations. And there are all kinds of techniques for doing this. So given enough data, deep learning can approximate any function in the world. That's kind of the claim. It's a universal function approximator. Given enough data, I can approximate anything. I can make this thing do anything. And it actually works. So right now you have these models, and this ECMWF is the European Center for Medium Range Weather Forecasting. It's widely recognized as the gold standard in computing for a week to 2 weeks, what's called a medium range weather forecast. NOAA does one, various other countries do one, but this is considered the gold standard. these pure machine learning models, which have been trained on their own data. So you take the ECMWF puts out its historical data going back to the 1960s of all the, they call them hindcasts, so all the forecasting data from the past. You can train on this data, and the machine learning can reproduce exactly, can emulate these systems, and there is no notion of understanding anymore. There's no physics in this. It's purely mathematical relationships, statistical relationships. And right now you see that it's showing all these, something called ForecastNet here, something called GraphCast, something called Pangu Weather, and something called AIFS. These four are pure machine learning models. There's no physics, there's no theory, there's nothing. And they're just as good. And they're very cheap to run. They're expensive to train, but actually running a forecast is very cheap. Same thing that takes a supercomputer at ECMWF or at NOAA. Typically a 6-hour forecast will take about 1 hour of computing on the whole machine. You can do it on a single GPU now in a few minutes. That's the change in the amount of computing required to produce a forecast is changed by like 3-4 orders of magnitude. It's an extraordinary change. It completely changes how we do things. Things to note, lot of these models, most of these models are in the private sector. GraphCast is produced by a company called DeepMind, Pangu Weather by Huawei, ForecastNet by NVIDIA. So this paper, the Financial Times wrote about this, let's say a little over a year ago. If all forecasts come from private companies, then essentially meteorology is no longer considered a public good. I mean, for us, just normal people, it may not matter. You're looking at your phone for a forecast, you'll still get the forecast. But for farmers and all, it matters a lot if they have to pay huge amounts of money to get an accurate forecast. All the models, as I said, were trained on this data set called ERA5 that comes out of ECMWF. That's a historical climate record for the past 60 years or so, and they're learning to emulate them. But they're dependent on this. This data is produced by a model. So it's not, even though they're saying, I'm not using any physics, I'm using pure machine learning, they're indirectly dependent on that, but they're working on it. So, and as I said, while training is expensive, inference, which is actually running the forecast, is really cheap, really cheap. So let's say that the NWP or the numerical weather prediction problem has been solved. What does that mean for climate? Climate is a different problem altogether. There are many sources of uncertainty. So in a forecast model, you're dealing with this initial condition uncertainty. If you know the initial conditions well, can I make a forecast is the question. Even that is not fully easy because of this phenomenon that we call chaos. Chaos means that even a very tiny change is called the butterfly effect, that was actually coined by the former director of GFTL called Smagorinsky. And Lorenz, who was a professor at MIT, borrowed the phrase from Smag and used it in a talk. And the talk was titled, Can the flap of a butterfly's wing in Brazil cause a tornado in Texas? In theory, the answer is yes. Any small effect anywhere will propagate around the world and it will have an effect in some other place. So that's shown as orange as a chaotic uncertainty. So it's very high in the beginning, and then over longer periods of time, that is not the biggest source of uncertainty. The second is scenario uncertainty. This is human actions. We're certainly not trying to model humans as part of the climate. The effects of what industrial civilization does in terms of emissions and whether it's aerosols, pollutants, or whether it's CO2, we can measure those. But like actually predicting what will happen is not part of the climate model. So the scenarios are all scenarios. We say if we do, they're called socioeconomic pathways. So you can have a world, you can postulate a world in which there is just conflict between power blocks, or there can be cooperation. So you can assume a multilateral world or a world of purely power blocks, and each one will give you a different scenario. And from using those models, you can predict not predict, but you can write pathways for what emissions might look like. So if you go out more than a few decades, this uncertainty becomes the largest. Between controlling carbon emissions and not controlling carbon emissions, the gap is huge. I'll show some examples in the film. The last thing is what we call epistemic uncertainty. It's what we actually don't understand. And that, as you can see, is also a big part of this. We have only one trajectory. That's the only thing can actually measure in the real world, what actually happened on this planet Earth over the last 50, 60 years. Now we're talking about all kinds of different uncertainties. physics with parameters. If you change a parameter, it's going to behave differently, and you don't know what the real value is. So you have to explore that uncertainty. You still have to explore this chaotic uncertainty, which is the butterfly effect, and you have the scenario uncertainty. You have to use models. So models are not just tools for prediction. Models are principally tools for exploring counterfactuals, things that do not happen. That's something to keep in mind. That's really what we use for, because we cannot and do not wish to do experiments on the real planet. We're doing one, of course. What we're doing right now, you can consider continued emissions is an experiment. I don't think it's turning out well, but it's a different story. So climate has different problems. So it has to generalize outside the training data. The largest volume of data you have goes back, generously, you can say the satellite era, 1957 is Sputnik. So we have about 60, 70 years of good data. For the ocean, we have even less. We have a few decades worth of very good ocean data, especially at depth. So you have to generalize. Your machine learning is very good at reproducing whatever is in the training data. It's not that great at generalizing, so you have to generalize. You have to be able to quantify all these sources of uncertainty. And you can do it in various ways. So basically what we do is, the one approach that's being tried is that you build these very, very high resolution simulations where you're actually simulating what's going on in the clouds. You cannot run many years of that because it's too expensive, but you can learn from those. If you can produce some training data, so you're doing machine learning, but you're machine learning not on real world data, but on the output of a model. So in the output of the model, you can explore counterfactuals. So it's using essentially what we call synthetic data for training the machine learning. And what we want to do is to be able to do this at multiple levels. You should be able to produce detailed models because sometimes that's needed. And sometimes you need to zoom out and unfocus your eyes and look at the overall behavior as a system as a whole without worrying about every little detail. You need to be able to do both. We have to worry about how long these simulations take to run. They're actually quite expensive. Running these global scale simulations, the GFTL computer, for example, takes the same amount of energy as 1,000 households in New Jersey. And we use that entirely for modeling the climate. We have to worry about that. But again, machine learning, if it is successful, will allow you to do the inference very cheap. So we are doing this coarse graining, which is what we are trying to do with the machine learning. So you build very high resolution simulations, as I said. This is a GFTL model running at a 3-kilometer resolution on the whole globe. That's very, very high resolution. Typical, as I said, is around 50 to 100. And you coarse grain the data down to 50 to 100. You're understanding the aggregate behavior of these small scale phenomena, and then you're trying to run these low resolution models. So machine learning is very good at that. So what it does is it takes complex data and reduces it to a few elements, which are called in machine learning lingo features. So you're trying to produce a small set of features that describe all the richness of your data. And the smaller the set of features you can get to, the better. So for example, facial recognition and all that works like this. So what a face is has been distilled down to like 7 numbers. And then using those 7 numbers, you can construct any face that's in a database of faces. Not only can you do that, you can generate new faces. You can take the face of this person and that person and see what their offspring would look like or something. So you can put a face that's somewhere in the middle of these two. So you can create all these synthetic faces. I'm sure you've seen lots of examples where you're shown faces and asked to see whether it was AI generated or a real face. Hard to tell. So we are doing imagine the same thing for a climate model. So you have 2 different kinds of climate model output in your training data, and you're trying to say, can I describe both of these situations using the smallest set of features? And then I can use that feature set to actually explore all these counterfactuals. So if I can produce these emulators, which is a small set of features that can encompass all the richness in my data, then I can use that. So this finding the essence is what we're trying to do. And this is an example that came up in some of my conversations this morning. Most of our training data, as I said, is present day. It's the last 50, 60 years. It's definitely since the Industrial Revolution. And I showed you the whole climate record of the planet. It's changed a lot over time. There were lots of things that happened. Traditional models, the physics models, are usually not very good at reproducing these past climates. So here's an example. So I showed you that little spike, which I call the PETM, or the Paleocene-Eocene thermal maximum. In that period, as I said, the temperatures, we have some ways of measuring past temperatures using isotope ratios. I won't get into the details of how you know what the temperature was, but we have fairly good evidence that near the poles in Antarctica, the temperature at that time was typically 17 degrees, and in the ocean, Arctic was completely ice-free, and the temperature there was 23 degrees. It's about a few degrees warmer near the equator, but generally there is a very slow temperature gradient. We call this an equable climate. The temperature is pretty much the same everywhere. All our models still try to create a. I don't know if you pay attention to the continents here, they're not very hard to see. They don't look like present day. You can see that India is still somewhere in the middle of the Indian Ocean. It has not yet, it sailed off from Africa. It has not yet hit Asia. Australia looks very different. These two, North and South America, are not joined. There's actually the Isthmus of Panama does not exist. There's open water here. So if you put in all these changes, you still don't get the circulation you want. So there's not much data, first of all. The models are not very good. So we cannot really it's not very clear how you're going to study these kinds of climates using machine learning, but we can use it for training and testing. So it's kind of important to keep this in mind. Now we move into what kinds of problems we want to do for the future. And here, again, what are we going to use the models for? So I'll divide the classes of problems we want to do in the future into two kinds. One is about adaptation to existing climate change. So some changes are coming. We're already committed to a certain amount of warming because CO2 stays in the atmosphere a long time. All the CO2 that we have emitted over the last few decades, it won't, even if you shut everything off today, it won't disappear instantly. We know that from COVID, for example, when we did shut everything down for 2 weeks and the carbon balance of the atmosphere didn't change very much. But there are certain things which we can. So if you look at, this is water, looking at maps of water. So there is a beautiful satellite instrument called GRACE, which can measure not amounts of water under land, but it can measure changes in water. It can measure an increase and decrease in underground water. This is water you cannot see on the surface. And blue areas are places where underground water storage is increasing, and red is where it's decreasing. You're probably aware that Southwest United States, which is this blob here, has undergone drought for several years. So people have been relying a lot on aquifers. There's a big aquifer here called the Ogallala. And so the water table has been alarmingly lowered in places like Arizona and New Mexico. Same is true in India. And northeastern India it's a wheat growing area that has changed into a rice growing area in the Punjab. And rice is very water intensive. And again, if the monsoon rains are not enough, people rely on underground water. So there are places where water is being depleted. But if you look at these various places where there's water-related troubles, changes in availability, there's two kinds of changes. One is what I said, how you manage your surface waters and your underground water. So this is all very human problems of how you manage resources. And the others are natural changes. Precipitation is changing. Some areas are becoming more drought-prone and some areas are getting excess. And even in the drought areas, you're probably aware that there's a trend towards having even if the mean amount of rainfall doesn't change, you have a lot of extreme events, extreme rainfall events. In the Indian monsoon, for sure, it appears that the same amount of rainfall is falling, but it's falling in the spiky pattern instead of evenly. And if you look at it, you'll see that the different hotspots around this planet have been classified as probably due to climate change, probably due to direct human impact, and that is how you manage your water. And probable natural variability, it's just a fluctuation that will go away in a few years. So if you want to know how to adapt to climate change in particular, I think people will be dealing with either too much or too little rain in many parts of the world. You can run models with enough data to kind of study these things. You can do predictions coupled with hydrology to see what places are at risk for water. So in my new role, we are funding some work in this area. When it comes to carbon, it's a different class of problem. And here I'm calling it, what we are working towards is something I'm calling a policy attribution framework. So again, I'm taking the very optimistic scenario, extremely optimistic scenario that we are going to do something about the carbon curve. There's no evidence that humans are going to do it, but let's assume they do. Okay, so you want to bend the carbon curve, you're going to take some actions. Plant a tree here, reduce, move to renewables over there. Relying on hydropower, you have to worry about, is there enough water from a hydropower? So there's a set of linked problems, right? So typically it's been shown, this is a famous paper from 2017, which he updated for us to 2021 or so. So you have these fluctuations of carbon. This is carbon emissions in the growth rate in the atmosphere measured over some decades. And it varies. Assuming that you don't know the causes for this variation, so you just treat it as what I call weather. It's just noise, it goes up and down. And then sometime you say, okay, we're going to take some action about the climate. I'm going to reduce my emissions at the rate of 1% a year. Now you see that given this natural variability, so there's a 1 standard deviation band is this big, and the 2 standard deviation band is that big. For me to see the signal of my carbon reduction, and to say confidently that it's not noise, it's an actual reduction in carbon, and I can measure it, it would take me on the order of 10 years. So this is definitely a disincentive reaction. If you say, I want you to take these actions to reduce your carbon emissions, but I won't be able to tell you for 10 years whether what you're saying is what you did is a good idea or not, I don't think that's going to work very well. So we're trying to see if we can work towards something where we can tell people what the anticipated policies or actual policies, what their effect will be on the carbon cycle, but we want an answer very much quicker than 10 years. Like we wanted to change it by an order of magnitude. So we're funding an amount of work to understand the carbon cycle better. It does matter a lot because of several reasons. One is the land carbon sink is changing in ways that are, to me at least, somewhat alarming. So here, a sink means carbon coming out of the atmosphere and being held in the land surface. So it means then it's sequestered in the land, it stays out of the atmosphere, it doesn't cause as much warming. So a negative sign means the land has become a source rather than a sink. So if you see, these are different ways of doing this, and these two are the lighter curves are for the tropics. In the tropics, depending on, so this is the temperature, there's a natural cycle which is called El Nino, the ENSO, the southern oscillation. So it's sometimes the warmer and sometimes cooler in the Pacific Ocean. So you see there is a linkage between that. Whenever it's warm, the tropical forests turn into a source. That is, they're emitting more carbon than they're absorbing. And when you have a cool period, which is known as La Nina, it turns into a sink. That means they're emitting less carbon than they're absorbing. So we had a period over the last few decades when we had a consistent series of La Ninas. You may have read about it. We had 3 or 4 consequent La Ninas without having an El Nino in between. During the period, the tropics appeared to be a sink. But again, last year they flipped and became a source. When it comes to mid-latitudes, these are 2 different methods of measuring the same thing, but they kind of broadly agree. So I'm not going to get into the details of that. You're seeing a broad decline in the land carbon sink. So the land's ability to absorb carbon. So it's true to an effect which is called CO2 fertilization. If you increase CO2, you're not only increasing the amount of plants, but the rate of photosynthesis in plant leaves increases. So that's a negative feedback. So the more you increase carbon, the greener the planet gets. It's called global greening as well, because the rate of photosynthesis increases. But the rate of that increase may be slowing down, which is why you're seeing the sink decline. The other thing that's happening is that the forests are increasingly disturbed, meaning that human behavior is actually affecting what happens to forests. In particular, what you've seen, and it's a headline event all the time, including in the last few weeks, the way we handle trees, we are making them more prone to large fires. And the Quebec fire in particular from 2023, which I'm sure you smelled the smoke from here, was one of the largest carbon events of that year. If the Quebec fire were a country, it would be the 4th largest carbon emitter in 2023, after China, US, and India. That's how much carbon that one fire, which it's an event, but it lasted weeks at least before they could put the fire out, because it's a lot of dense old forests that have not burnt for a very long time. So these things are quite important to measure. And if you think about their future, I'll leave the ocean out for a minute and talk about the land. So I told you about these scenarios. So we're trying to put various scenarios and see how the net land carbon sink might evolve into the future. So, and you're coming up with various scenarios. Some show a decline, some show an increase. But these error bars are kind of important here. if you take different models, so 2 or 3 people have built different models of the land system and they each do a comparison, the uncertainty between these models is as big as the uncertainty between the scenarios. It means we don't really understand all the drivers of this land carbon sink very well. So that's really the key issue that we're trying to solve here. We need to understand that better. In the ocean, it's a different. So I showed you this thing which is called the meridional overturning circulation, and you can look at it at various ways. You can look at it as just this conveyor belt circulation. If you go into more detail, you'll find there are some details. The warm water from the tropical Atlantic actually is moved not only northward, but is also moved eastward by the Gulf Stream, which is what gives Europe a much warmer climate than America, because all this warm water is actually goes over there. And there's some speculation about whether this can actually collapse. Like if that overturning circulation collapses, the Gulf Stream will shut off and it'll turn Europe much cooler than it is today. It'll become the comparable latitude to, let's say, London would be like northern Labrador. So imagine that London has a climate like northern Labrador. So that's kind of what we're looking at if the Gulf Stream shuts off. So there's a paper that came out which made a lot of news last year where this Ditlevson, they actually looked at certain dynamical signals and said there is a likelihood that in this century, in the middle of this century, the AMOC, the meridional overturning, would actually collapse. It's not clear. The details, there's almost immediately a second paper came out saying that the data that they used is not sufficient to constrain the problem. So it's not a solved problem, but it cannot be ruled out either. So these big sudden changes to the climate, we are destabilizing something. We're poking the bear essentially. So should not be surprised if the bear bites back at some point. So this is kind of my summary. So I'm trying to introduce you to ways in which we're using climate models today, and the fact that machine learning has actually transformed numerical weather prediction. Actual forecasting means that we are taking it seriously for climate as well. But we are trying to do this, and my first phrase is planets are building up. We are not just, we are thinking of the planet as an engineering problem, but it doesn't work like that. It's a living system. It reacts to the changes you make. So don't assume you can do interventions. So that's something that we need to explore solutions. The planet you have to allow the planet to respond to the solutions. The issue is that it responds in the atmosphere rather quickly, but it also responds very slowly in the ocean and land. The models have become very, very detailed. I have some problems with very detailed model, and they're best illustrated by the story from the Argentinian writer Jorge Luis Borges. His parable is just a one-page short story. It's called On Exactitude in Science. You can find it by Googling. And there, it's just a parable, and the story is that the cartographers in a certain nation, they build these maps which are at the scale of the map of the country is the size of a county, the map of a county is the size of a city. It's a very detailed map. And they say, well, we can do better. We're going to produce a map that's one-to-one scale. And they produce a map that is on the same scale of the planet and of the country, and it has everything. And then the rulers of the country say, well, what good is it? And they conclude it's not very good. And so they abandon the project. And then the end of the story, they say that homeless people use fragments of the map as blankets in the winter. That's how the story ends. Sylvie and Bruno, Lewis Carroll had a similar story, which I found later, where somebody says, I have the same thing. I have a map of let's go for a walk. I have a map that's one-to-one scale, so I can take you on any path you like. And then the guy says, well, okay, show me the map. I say, well, I can't actually show you. It's too big. I can't actually show you the map. Anyway, our models are getting like that. That's the whole point. Our models are getting so complex that, yes, maybe you're representing everything, but I don't know what the model is doing. It's just doing some complex thing, and I don't understand it. So you have to compare models with other things as well. So many people have written a lot about this. Naomi Oreskes has written about this in Harvard a lot. The trust comes from, you have to understand individual process, and then you have to compare it with other lines of evidence. Predictions are useful when you know what to do. When you don't know what to do, when you don't know what the solution is, predictions by themselves won't do. You have to explore all your scenarios. That's why the counterfactuals come in, and it's very important in machine learning because the real world data does not contain those counterfactuals. So what we do is we build all these thousands and thousands of simulated planets. And in some cases, we try to use them for training as well, training machine learning. But remembering that you must be able to go outside the bounds of observations and then you have to derive these simple models for some problems and complex models for other problems. So you need a whole, what we call a hierarchy of models. Now, I'll point you to a paper because, I kind of surveyed how it has evolved from the time of Charney to today. So if anybody's interested, it's a paper written for a non-specialist audience, which I hope you like. So thank you. I'll stop here.
We have time for some questions. That's okay with you?
Absolutely, yeah.
All right.
Yeah.
I'll let you take the questions as you like.
Okay. Yes.
Thank you. That was most fascinating, particularly also looking into the history and how that evolved and the recent developments. So I'm wondering where we will be next Monday with the ML models just in a week from now. It's really exploding while you speak. But specifically, one question is, you touched most upon kind of a global climate change models. From a medical health background, what we're interested in is extreme weather events. You mentioned droughts, but also heat waves, etc., because they will have the strongest impact on adverse health outcomes. It's not the 1.5 degree average, it's the heat waves in France, the first ones, etc. So how good are these models in, say, globally predicting the frequency of extreme weather events defined by some way? And how good will they be to kind of regionally predict those extreme weather events?
So that's an excellent question. There's not an easy answer to it because by the nature of these extreme events, they're rare. So there's not many. The rarer even the less data that the machine learning has seen. So I would have less confidence in its ability to predict. But people are developing mathematical techniques to take from the real data set, create a synthetic data set that has a greater frequency of these extreme events. And you can even put compound events into it, a simultaneous fire and a rain event, for instance. You can do things like that, which also have, which simultaneous heat and humidity events have a lot of adverse health outcomes, for example. So you can mathematically boost the number of these extreme events you see, and you can train on that. And then you have to, these techniques allow you to reverse and go back to the original return period of those same events. So there are methods for doing this. So people are working on these sorts of issues, yes. Yeah. And as you say, it's a very fast moving field. So anything that I say is not done today, by next Monday, it might be solved. Yeah. Yes.
Oh, yeah, thank you. That was excellent talk. Thank you. I'm on the social science side of things, and I'm curious, you mentioned the shared socioeconomic pathways of that the IPCC included in the last year, 8 or 6. I'm curious, that sort of gets into my area.
Mm-hmm.
I'm curious sort of what you think about them, anything you could say about them, and also what your larger how your sort of larger community sort of has responded to that innovation in sort of thinking about the future.
Yeah, okay, so thanks for that question. So until AR6, we relied on these things called representative concentration pathways, or RCPs, which are purely about CO2 and to some extent aerosols. And now there is some social theory behind the way you're constructing these. That's why the SSPs came in. To be honest, for somebody, I'm sure you would find it hard to take those things very seriously. Even there, related to what you said, the data changes very fast. There's an anecdote I can remember. Yi probably remembers from the last go around, is that in 2014 or so, they gave us they gave us these projections that we can input into our models for emissions. They gave us some output curves based on a certain pathway in China. And it takes us a couple of years to get our act together after the forcings are given to us to actually run the simulations. By the time the data showed that the Chinese sulfates had plummeted, and that meant that the emissions scenarios we're using did not correspond to the real world. So I mean, I would not take them, there's this phrase that people use, right? Take them seriously, but not literally, rather than literally, but not seriously. So I would, they're useful for showing you a span of possible outcomes, but I would not take them literally beyond that. Is that a fair answer? Yeah.
Thank you.
I think there was a question behind you as well. No? No. Okay, maybe not. Anyone else? Some people I don't see it all. So yes, hi.
I'm not someone from the field, but I understood it very clearly.
Thank you.
So my question is very fundamental. Like when you make these models predictions based on weather and climate change, are there any fundamental parameters that you use to validate the predictions that your model estimated?
Yeah, so that is for climate change. I mean, that is a hard problem, right? Because you're trying to say what will happen decades from now. So you cannot do an actual verification for decades in principle. But that's where the paleo data all comes in. So I showed in the very first graph I showed, for the last 10,000 years, you had an extraordinarily stable climate, and then we've spiked the CO2. So it's unprecedented in recent history, but it is not unprecedented if you go back further than that. So paleo climate data is a very, very important validator of what we know and don't know about the climate. Unfortunately, people don't take it seriously now, and they say it's it's just something in the past and we don't need to worry. But in terms of knowing what a warm climate looks like, the real evidence comes from that old data, but it's very hard to get at. As I said, you can't actually measure temperatures, so you're measuring it by looking at some shells and tree rings and ice cores and trying to see something, trying to deduce from that. It's not an easy problem, but it's a very fascinating problem. The ways in which people reconstruct old temperatures and rainfall events, I just love it. It's just beautiful work.
Yeah, you talked about issues related to water supply, having potable fresh water or fresh water available for agriculture. And mentioned that your institute, the Climate Institute, is funding some studies on that. And I just wonder if you can talk a little bit about where you think that research needs to go, and what Schmidt Sciences is doing in terms of funding that kind of research.
Okay.
Because it's so necessary for life as we know it on this planet.
Yes, absolutely. So we've narrowed in on two areas we're really focusing. And as I said, we're able to fund a lot of work, but climate is so vast and encompasses so many things. We have had to pick and choose. And I'm sure many people's favorite problems is left out of the portfolio. But freshwater and carbon are the two most important ones we've looked at. So water, the way we formulated is that it's, people talk about the food, water, energy nexus. It's necessary for food and for energy both. I don't know if you saw the recent headline that Ecuador had been relying a lot on hydropower for its carbon transition. And they're in extended drought, so there's not enough water in the rivers. So these are all really hard problems. But beyond that, the water is also, natural systems also need water, so we should not forget that natural systems are also competing with us for water resources. So this is a problem which is particularly hard because we cannot take water management out of the picture. So knowing what happened to water in a particular region you have to know how the water was managed. And all of it depends on what humans have been doing for the last few decades. Are they allowing pumping? Are there any restrictions on pumping underground water? These sorts of questions. Their overground reservoirs, are they well maintained now? So it's very hard for me today to answer questions, but in some areas it's much easier than others, like that map shows. Some areas the effects are obvious. You're taking out there's a drought, so you're taking out underground water and you're going to run out of water. Some areas it's less easy to know these things. So we are trying to challenge people to come up with the same way we do this historical record of weather, to come up with a historical record of water, so that we can go to any region and ask the question, why is the water situation here today? Is it because of the same thing that showed the guy? Is it because of just variability in the climate? Is it because of long-term decline in precipitation, or is it because of the way you manage water? So I'm going to be a little long-winded here, but let me give you an anecdote going back to the 70s. So Sahel, which is the green border at the southern edge of the Sahara, underwent a drought in the 70s. And if you read the early literature on that, the word that people used was desertification. They blamed the people there for mismanaging the water and causing the deserts. It turns out in work that Yi and others have done is that that's not the reason. The reason is actually that changes in aerosol concentration over Europe actually affects precipitation over there. So it's actually it has nothing to do with the way local people were managing, but it was blamed on local water management rather than changes to the climate. So we want a historic record where all these questions can be answered in a rigorous way without having to bring ideology into it and all that. So that's kind of what we're hoping to get with the water program.
Thank you for your talk. Is there evidence that at some point of trying to bend the curve, there will be no turning back point where no matter how do we reduce emissions, we still kind of get worse?
Well, there are many people are speculating about many things. I don't know if you've seen the Snowpiercer movie, but one thing is that you can cause a runaway cooling also, that you can actually start the next ice age off, right? So that's also been, so intervening is definitely, you can think of many things. Is there a place where if you, to the extent that I understand it, there is one thing that actually makes our life somewhat easier. The global mean surface temperature is directly proportional to the cumulative emissions. That seems to be a well-known fact. That seems to be just true. So the cumulative emissions, if you stopped everything today, the cumulative emissions would stay where they are, and then they would go through a slow decline on a time scale. For methane, it's around 5-6 years, and for CO2, it's closer to 30-40 years. So it will slowly decline back to pre-industrial levels. And then in theory, because of this proportionality, I think the temperature would come down in this proportionally to that. So there does seem to be a robust link between cumulative emissions of CO2 and temperature.